start. Okay. So, okay, I think I have made the announcement. So, so we are meeting again, and it sucks. Okay, so so this course, so this course is on analysis, and this is supposed to be a very, basic analysis which every mathematician should know. But since you have already done some metric spaces, I will start with metric space, and I will start make the basic definitions. I will go through, but whenever, if you think that you have already done something, or if the proof is already, you know it, then I may not do it. Okay. So let me see what I can do more to, fill this course. Okay? So instantly, people have problems. I saw your comments. People have problems with my handwriting, but I don't think I can improve my handwriting at this stage. But other things, like if I make a mistake, I don't think I will make a mistake in mathematical argument. Maybe I will make it and correct it immediately. But if I make a typo or something, I think it's better you should also be, be conscious about it and tell me. Okay. So I may make some mistake, but see, the one thing is I can keep a notes and then copy it or something, but then it doesn't work for me. Okay, I have to do it like this. Okay, so on the other hand, if you have any problem or if you want to discuss with me, we can fix Wednesday after the class, 5:15 or something. We can discuss it in mail. Okay, I will be available for that. Okay, so we want to discuss these objects, which are some abstract objects. So, so why do we want to do? So what is analysis? So when we analysis, of course, analysis, there is no clear definition of analysis. You have done mostly calculus, which is part of analysis. You have done probability, that's also analysis. But differential equations, partial differential equations, all these things come under analysis. Analysis is very vast, and there is no question that it's a very useful mathematics. So, but the basic thing in analysis, what one does is something like computing the limit. There is something called limit you have to compute. Okay? So, to compute the limit, you must have seen this definition. So, if some xn will converge to some x, if they are all real numbers or complex numbers, then you know that what it means. You know what it means. That xn converges to x means, that is one thing. It is just that after some time, xn will be as close as you want to x. So that as close as you want is given by some epsilon. So if you choose an interval x minus epsilon, x plus epsilon, then all these xn's after some time will be in this interval. That you can write it in other way. There exists a n such that for all n greater than or equal to n, this xn minus x is less than epsilon. Okay. So this is something like distance between x and xn and x. Okay. This notion of distance we want to generalize, and we want to generalize for any abstract set. Okay. So you take any set, then you can define something called a distance function which satisfies some three properties. Then using that you can define limit. Once you define limit, you can define continuity. When you have more structure, you can even differentiate, but it's not always possible. But you need more structure. Okay. So you can do other things also. You can talk about compactness, everything which is based on the notion of distance, limit, and all those things. Whatever is possible using this notion of distance, we will develop. Okay. We will develop those properties, and we will study that. So the question is whether can we define it on any set. Okay. But what is set? It is not clear what is set. Have you gone through the discussion of set anywhere? Okay. Set. What is a set? We have some funny way of writing. Just put two parentheses and So what is okay? It is not clear what is set. Okay, there are some axioms for set, but then it will be a class on set theory, and of course I also don't remember now. So there are some axioms for set theory, but then so for this course we want to use some particular. So usually set is something like you can have these parentheses and then you can list down the objects, you can list down the elements of the set. That's one way of defining a set, and then it should be well defined. For example, if you say set of all pop songs or something, it so it is not clear. Somebody may not agree with you that it's a pop song or something. They may say something else. Oh, no, it has some rock element or something. Then it will be it will not be clear. Okay. So usually something like when you have a set, you will usually say that some x satisfying some property, or some x in x, some other set you have defined already, and then this x satisfies some property. That property should be well defined. What does it mean by well defined? All of us should have the same interpretation for that, and we should be able to write it rigorously. Yeah, usually, exactly. But beyond all these things, usually we have in the set theory, we have the basic operations. Those definitions should be based on that itself. Okay, I mean, whatever the set you define for those definition, everything, it should also be based on set theory itself. Okay, let me make it clear what I mean by that. Okay? So, for example, if you can you define any set just like that, any set. So you have you know that set can contain set, not just set can contain set. Set can contain sets as elements, not just a subset. Okay, you can take some two sets A, B, and you can form a set like this. Eh? Yeah, but the question is, if you have a set S, is S itself, can it sit inside as an element of S? Okay, why do you think it's not possible? You take, suppose if you take set of all sets, if it is a set, then that has to be a set, right? That is not, so that there is some problem with that, right? So we don't know whether S is element of S, we don't know that. Okay, whether there exists a set such that S itself sit as a element of S, we don't know that. But we know that this is true. There exists set where S is not an element of S. Okay, almost all the sets we deal with satisfy this property, right? So we know this. So let us take this collection of all those set. Yes, S is a set. Okay, S is a set such that S is not an element of S. You call this like this. Okay, call this script S. Okay, this is clear, very clear definition. You said we should make a well-defined, rigorous definition, which is clearly a rigorous definition. You whatever the set which is possible, you take all those collection of set such that S is not an element of set, and we know real number, complex number, everything. Now the question is whether this is a set. Is S is an element of S? This is the question. Okay. So this is the paradox. If S is an element of S, then it has to satisfy this property. So S is not an element of S. Okay. Right. So if S is not an element of S, so it should negate this property. It should not satisfy this property. So that's simply S is an element of S. Okay. So S is an element of S if and only if S is not an element of S. Okay. So this is a paradox. Okay. So we cannot the object sets are quite complicated. Okay. So it's not so. But then all our mathematics, everything is based, the foundation is based on set. Okay. So you have seen the construction of natural numbers. You have seen it. How did you construct? Okay. So you have seen that. Okay. You have seen that. Okay. So to do that, there is a basic assumption in mathematics that see, how do you define empty set? Set without any element. But then you can write that as using some definition. You can write, for example, you take some set and all those x in x such that x is not equal to x or something. That will be an empty set, of course. Okay. But then this will depend on this x. But then you can, using set theory logic, you can prove that this does not depend on x or something. But still, you have to assume in math, you have to assume that empty set something exists. Okay. This is the basic axiom of mathematics. Okay. Axiom of mathematics or analysis, whatever you say. So the first axiom is empty set exists. It exists. Okay. But this is not enough. This is like an apple exists or anything exists. Okay. I mean, like God exists or something. But then you need to assume something more. That is, this empty set is not equal to the empty set containing this one set. This is a very reasonable assumption, empty set which has no element, and this has some element there. So these two are not equal. Okay? This is the basic assumption. So once you have this assumption, then you can define natural number. Okay, you can define natural number as all finite set, for example. But what is finite? You still don't know cardinality. See, in reality, mathematics is an abstract thing, okay, abstract world. The objects are abstract. For example, in reality, there is nothing called number 2, number 3, right? In reality itself, we only have 2 apples, 3 oranges, or something like that. Okay, 2 planets. Those things only we have. We don't have anything called 2. 2 is an abstraction. 2 is the cardinality of the set of 2 apples. So you need, it's a mathematical object. Okay? 2 is not something, something which is in the real world, which is not there. It's a mathematical object. Okay? So like that, you can define all. You can take the collection of finite set, and you can say that then you have to say what is finite. But it's easy to define infinite it's easy to define infinite. But I'm not writing all those things. What is infinite? In set is infinite if there exists a proper subset where there is a bijection of that set into a proper subset of that. Okay, that you can call it. If you have a set S, okay, then you have a S naught contained in S which is not equal to S. Then there is a bijection between that. That is what then the set is called infinite. Then finite is something which is not infinite. Then you take the collection of all finite set. Okay, collection of all finite set. You can define that to be natural number. But then we have difficulty. Then you can take disjoint union as summation and all that. Okay, as sum of 2 natural number. It's easy to define that. Here it's slightly tricky since you have seen it or something, and that's not our point. I will not go through that. Okay, so natural number n is defined by this. You take phi 0 equal to phi, and then this is 1. These two are not equal, of course. Okay, maybe 1 is equal to this. And then 2 is equal to phi this. Okay. Generally, n plus 1 is equal to n, which is a set, union the set containing n. Okay, which makes sense. Okay. So then you can define addition and other things, which is associative and all that. Okay. So once you have this, you can define Z. You can just take plus or minus n if you want, just like that. That's enough for us. Or you can define a tuple mn with some equivalence relation and other things. Let's not go through that. Okay. So Z you can define. So from this you can define Q. Okay. Q is just all those A by B, where B is not equal to 0. Minus. No, it is just this minus you are asking, or the operation minus you are asking?
How do you like?
No, operation minus is m plus minus n, that's all. Plus, once you have plus. Oh no, this, I haven't defined addition, for example. Addition is something, you have to go through that. Addition is defined something like this. It is like n. See, there is something called successor of something. Okay, n plus, if you take successor of m, then this is equal to, you have to take this axiom. Okay.
So these are like the axioms that we have to.
Yeah, you have to go through the axiom. Okay. Either you have gone through, and this is not what we want to do in this course. Just take it for granted what is n, which is not very difficult to agree. The whole point in n is, there is no complication in n. It is just, you can take it at 1, 2, up 1, 2, 3, up to, up to infinity. Up to infinity is not included. You can take it like that, and you know addition and all those things. What is not clear, what is real number is not clear. Even intuitively, it's not clear. How do you define all real numbers? That is not clear to us. Okay? We have to go through it because you want a rigorous definition, set theory, and all that. You are doing this for n, but that is not our point. We don't. When we agree, we accept that there is a n, there is a z. But even then, it is not clear what is real line. We know what is q. Q is just a by b with an equal. Q tilde is all a by b, where a and b are integers. Okay. And then you have to impose the equivalence relation, a by b equal to c by d. If you cross multiply, they are equal or something, then that will give an equivalence relation. If you mod out the equivalence relation, then this is all rationals. You get all rational. So rationals till here it's clear. Okay. Now we want to construct real numbers from rational. That's what I said. You can take all possible A by B, then you take the equivalence class. A by B is equal to C by D if BC equal to AD. Okay, that's an equivalence relation. You know equivalence relation and equivalence class and all those things, I'm sure. Okay, so it is just the equivalence class of all A by B. Okay. Okay. So let's fix here. Fix. Okay, we have Q, which we call rational numbers. Okay, and we have this modulus function. Okay? We have modulus function, which is clear to easily we can define. I mean, it is just the modulus of that. It is just if A by B is positive, it is A by B. If it is negative, it is minus of that. Okay, then you know that it satisfies the triangle inequality. All those things you can sit down and verify one by one. Okay, you must have done this. Okay, in the first course in analysis. So you have Q with modulus function. So the question is, what are all the real numbers? How do you get all the real numbers? You have all the rational numbers. Why it doesn't fill? I mean, why whatever you mean by real line? Why it doesn't fill? Okay. The point is you have something called Cauchy sequence. Okay, you have the definition. Okay, if you have a xn contained in Q is Cauchy, you know the definition already. If there exists, I mean, given epsilon, there exists n such that xn minus xm is less than epsilon for all nm greater than or equal to n. Okay. You have the Cauchy sequence. The question is whether all Cauchy sequence in Q converges. You know, there exist the examples of convergence sequence, you know, even 1 by n converges, and you have a lot of sequences of rational which converges to a rational number. Okay. The question is, you can take some, you can define, I mean, you can take the, you know, pi, I mean, you know what is pi, or you can take E, for example, then you can define 1 plus 1 by 2, or 1 plus 1 by 2 plus 1 by 3 factorial. This is x2, this is x3 or something. This sequence will be an irrational, this sequence will not converge to a rational number. You can see that. Okay. So considering, I mean, you can define the limit also as usual. Then you get that you see that you don't have all the limits of the rational sequences of rational numbers, which is contained in which is not contained in rational numbers. Okay. So how do you define the limit? So till now we don't have real numbers. Okay. So we only have rational numbers, and we have defined Cauchy sequence. So for a general sequence, Cauchy sequence, you want to define the notion of limit for it. I mean, which is intuitively it is clear. You have a sequence, and then the distance between xn and xm decreases and it goes to 0. Okay, so it should go to some limit. That's what, if you look at the line or something, it should go to some limit somewhere. If the line is continuous or whatever, okay, it should go to some limit. But what is that limit? Okay, in mathematics we do something very dubious. You call the Cauchy sequence as the limit. That's all. Okay, if we have a Cauchy sequence of if someone asks something, I said you define the limit to be that Cauchy sequence itself. I will definitely. Yeah. You have a Cauchy sequence. Yeah, you have a Cauchy sequence. We will see how it is defined and how it is well defined. Okay, it just works for our purpose. That's all. The limit of the Cauchy sequence is that Cauchy sequence itself. So how do you define that? So that is the construction. Okay, you take R tilde equal to all sequences xn, where xn, I don't have to define sequence, I believe. It is just a function from natural number to Q. Okay, that's what a sequence is. I mean, with the idea of function set, you can define all these things. Okay, we need not go through each and everything. So if a sequence is just a function from natural number to Q, okay, then you take all these sequences, n equal to 1 to infinity, xn is Cauchy. This is a set. You have rationals, and you take the collection of Cauchy sequences in rational. Okay, that is another set. Okay, so now you have now you can embed Q into this R tilde. Like if you have some Q, which is some Q in Q, and you take this sequence, Q itself, Q, constant sequence. Okay, constant sequence. So this Q is embedded in R tilde. Now you have a sequence of here means you will have a sequence of constant sequence, of course. Okay. What is the limit of that? The limit of that is the Cauchy sequence itself. Okay. I say it again. What do you mean by embed? It's just a function from here to here. It's just one, I mean, injective function. That's all. Okay? It is just the injective function. There is no more, no other structure we have. Okay? So from Q to R tilde, you just have an 1 function. Okay? It's just not onto. So you can just embed Q into R tilde. Okay. And then if you have a sequence, you can just define it like that. But the question is, there may be two Cauchy sequence which may converge to same limit or something like that. I mean, so it may, I mean, we may have, no, it's not just like that. You can have a sequence, I mean, the limit of a sequence is supposed to be a function. It should have only one, it should exist and it should have only one value. Okay. So there may be, it may, for example, if you take the, I mean, there may be same number can be same real number, whatever, same Cauchy sequence can be represented in two different ways. What I mean is the following. So you define an equivalence relation, defines equivalence relation on R tilde. So you have two Cauchy sequence, xn is equivalent to yn. Okay. If the difference minus yn goes to 0. Okay. Okay. So this gives an equivalence relation. Should I check? It's clear that it is equivalence relation. Xn is any sequence is equivalent to itself, and xn equivalent to yn equal to that, and xn minus yn goes to 0, yn minus zn go to 0, xn minus zn will go to 0. So it's an equivalence relation. Okay. Now you just define R to be R tilde with this quotiented with this equivalence relation. Q, which is a sequence. Yeah, no. R tilde is all Cauchy sequence. All Cauchy sequence. Inside that, I am embedding Q. Okay, so Q is embedded as constant sequences. Okay. Now, if you have, so, okay. Yeah. So this is what I want to call as R. Okay. R is just all Cauchy sequence in rational numbers, okay, with identified with respect to this equivalence relation. Two Cauchy sequences are equivalent if the difference goes to 0. Okay. Okay. R quotiented with tilde. Equivalence relation. You know equivalence class. Okay. You take the equivalence class which partition the whole set and all those things you know. So we have R. I mean, we will see this again as a completion of metric space again. Have you? I think you haven't seen. That's why you are asking questions about. You didn't go through. It was not done. That's okay. That's it. I don't know why it should be. It should not have been done. Okay. You have seen it. Some of you have seen it. Okay. That's okay. So it is basically that's what I'm doing. Okay. I mean, you should have asked one question. When I defined the Cauchy sequence, I took epsilon and then something. We haven't even got all reals. So what is epsilon? You should have asked. Epsilon is from rational. It's a rational epsilon. Okay. It's a rational. No, that's what. I mean, when I said epsilon, you should be just careful. It's only a rational epsilon we were using. Okay. Okay. So R is our R tilde, which is all those xn, the equivalence class, okay, where xn is in Q and xn Cauchy. And with respect to the equivalence relation. So, okay, we have defined it. And we will come to how to represent each and every R, we will come to that. But before that, the question is, we have to define sum of two real numbers, product of two real numbers. I will go a bit fast because these things are very easy and you can check it, okay. And then, I mean, real number is defined through axioms. I hope you have seen this in the first course. Axioms of real number. in the first course in analysis you must have seen. Okay, I mean I wrote that syllabus, so I mean it should be there. Okay, so all those axioms we should verify. I mean it will take a lot of time and it will be messy to verify everything. So I will just tell you something and then I will give it as an assignment, something. Okay, the Archimedean property or something I will ask you to verify as an assignment. Okay, I will give it as an assignment. Okay, so you can define first definition 1. Okay? You can define the equivalence class Xn. You have a Cauchy sequence. Okay, and you have defined another equivalence class Yn. You can just, you want to define it as Xn plus Yn. To define this, okay, to define, you have to verify that if Xn is Cauchy, Yn is Cauchy, Xn plus Yn is Cauchy. That is just clear, right? If Xn is Cauchy, then Xn plus Yn minus Xm plus Ym, okay, which is just triangle inequality, okay, which is just less than or equal to Xn minus Xm plus Yn minus Ym. So because of this, if you have two Cauchy sequence, then the sum is also Cauchy sequence. So you can define this sum, but that's not enough. You have to verify this is well defined, because sum x plus y is a function, right? It's a function. It's a function from R cross R to R. Plus is a function from R cross R to R. Okay. So if you take x, y, then it is x plus y. So if you have a Cauchy sequence here, you have to define it as a sum. You sum the individual element of the sequence. Okay. So we have shown the existence of a Cauchy sequence as a sum. You have to say that, I mean, for it to be a function, it should be well defined. Okay, the image should be unique. Okay, so for that, what we have to do is, if Xn, so this is what we have to verify. If Xn is equivalent to some An, okay, and Yn is equivalent to some Bn, okay, then Xn plus Yn should be equivalent to An plus Bn. Okay, we have to verify this. So is it difficult to verify? I think it's clear, right? Xn is equivalent to me, Xn minus An goes to 0, Yn minus Bn goes to 0, this minus this will also go to 0. So because of this is well defined. Okay, I'm not writing as a formal proof because I think, I mean, when I prove something, I will do it a bit more carefully. Okay, so this is clear. So this is a well defined. So this Xn plus Yn written like this is well defined. Okay, so plus is defined. Definition 2. So if we have a Xn in Xn Yn in R, okay, then you can define the product. So you call it this as X, call this as Y, maybe X bar, Y bar, okay. Then X bar dot Y bar to be just the product. Okay. So for the first two things, you have to verify this. To prove this, you have to verify the following. 1, if Xn is Cauchy, Yn Cauchy. I mean, these are all Cauchy sequence in rationals. Okay, so if Xn is a Cauchy sequence, Yn is a Cauchy sequence, then the product Xn Yn is also Cauchy. Okay, this you have to verify, number 1. Number 2, you have to verify that this is well defined. That is, again, if Xn is equivalent to An, Yn is equivalent to Bn, then Xn Yn, the product is equivalent to An Bn. The product An Bn. So that you have to verify. Two things you have to verify. So, I mean, I want to give the whole thing as assignment. Just say the proof orally, and I want you to write. Is that okay? That's one assignment. I want to give verifying all the axioms of R. R is a field, and other totally ordered property. I want to say the proof orally, and I want you to write it as an assignment. Is that okay? No, I will tell you what are all the things to verify, or I will post it as an assignment in the model. I mean, there are some axioms of real number which defines it. So you have to verify all these axioms. Yeah, so that once I give it as an assignment and I don't write everything, I can start metric spaces. Okay. So to verify that this So if xn, so first thing is if xn is Cauchy, yn is Cauchy. If xn is Cauchy, xn is bounded. First you have to verify that. Okay, xn is bounded. That's because after some up to n, after n, xn minus yn is xn minus xm is less than epsilon. So xn is less than or equal to xn minus xm plus xn. So the first n things there is you can take the maximum of that. So it will be bounded. Okay, so any Cauchy sequence is bounded. You must have seen this proof. Correct. No, here it's xn is equivalence class of Cauchy. Here I am saying I am taking an individual from the Cauchy sequence, and then I am just verifying that the product is also a Cauchy sequence. So that's what I said here. I didn't write it properly. If xn is a Cauchy sequence, yn is a Cauchy sequence, then the product is also a Cauchy sequence. Okay. Once you verify that, you can define the image to be that. Okay. You can define the sum to be that. Then you have to verify it is well defined. To verify well defined, if xn is equivalent to some an, yn is equivalent to some bn, then xn plus yn is equivalent to an plus bn. So the whatever the sum plus you have defined is well defined. Similarly, you have to do the same thing for the product. To do for the product, of course, you first have to verify that if you have a sequence xn, sequence yn, both are Cauchy sequence, then xn yn, that is a Cauchy sequence you have to verify. To verify that, first you have to, it's clear that you have to prove that if xn is Cauchy, then it is bounded. Okay. So similarly, yn is also bounded. Once it is bounded, you use the triangle inequality xn yn minus xm ym. This is what you want to show it's Cauchy. So you write it as xn yn minus xn, then mod xn you can take it out, that will be less. You must have seen this. Okay. So then using that you can prove that the product is also Cauchy. Now you have to verify that this is well defined. For that also you have to do the same thing. I mean, it will be the same thing you have to do, and you can verify that the product is well defined. So now the product is well defined, sum is well defined. Now we know what is the unit. The constant equals 1, 1, 1 is the unit. Okay. Now you have to find the inverse. Okay. Third, if you have a xn in R, an equivalence class of Cauchy sequence, you want to define the inverse of this. You call this as x. You want to define what is x inverse. Okay. To define x inverse, so if xn is equivalent to 0, okay, then you don't have inverse for 0. Okay. So xn is not equivalent to 0. Equivalent to 0. Okay. Suppose xn is not equivalent to 0. Then you prove that there exists n, and there exists n such that an is greater than, strictly greater than 0 for all n greater than or equal to n. If xn is not equivalent to 0, sorry, xn. Okay, I have started. Okay. So if xn is not a sequence, if xn is not equivalent to 0, it's not the 0 element, it's not in the 0 equivalence class. Okay. Then there exists a n such that xn is strictly greater than 0 after some time. It has to be strictly greater than 0. Strictly less than 0. Sorry, xn is not equal to 0. Right, sorry. Xn is not equal to 0. That's what. Sorry. Xn is not equal to 0. That's what I want to say. Sorry. Okay. So then you can define the inverse. Okay. Then you define x inverse to be 0, 0, 0 up to n. Okay. And after that, 1 by xn. Okay. And after that, this will be the inverse. If you take the product, it will be 0, 0, but after that it will be 1, 1, 1, which is equivalent to 1, 1, 1, because up to finite stage in a Cauchy sequence, it doesn't matter. Okay. Because these are all only tail behavior which matters. Okay. So because of that, this will be the inverse. So you have got the inverse. Okay. What else you need? You have got, I think it's a field now. So you can verify other things. It's clear. Other things are clear. So R is a field. Okay. Okay. Then you can define so you want to define the partial order. Okay. So R plus dot is a field. Okay. I mean, if I have missed something, you should please verify it. Okay, in the assignment. Okay. I don't think I missed anything. Okay. So now you want to define the partial order. Okay. So to define the partial order, So you have some xn. Okay. So if xn is, I mean, see, if xn is equal to equivalent to 0, if xn is equal to same thing as 0 sequence, okay, okay, then it is equal to 0. Okay, then I mean, then this is same as this. So if xn is not equal to this, okay, not equal to this, okay, then there exists after some time, it will be strictly positive or it will be strictly negative. Okay, so if x, so then, so we say that xn, this is greater than 0 if xn is greater than 0 for all, I mean, there exists a n such that xn is greater than 0 for all n greater than or equal to n. Okay. So this is the definition of a sequence, I mean, a Cauchy sequence being equivalence class of Cauchy sequence greater than 0. Okay. Now you define xn, some equivalence of a Cauchy sequence is greater than yn. Okay. If xn minus yn, okay, this is greater than 0. That's all. Okay. You have to verify this is a partial order, which is not difficult. Okay. So you have to verify it's a total order. I will pause for a second. Okay, so I will post all the other axioms and you can write it as an assignment. Okay. Okay. So once you have constructed rational numbers, as I said in the beginning, how we, once we have some set, using that set we will construct other sets. Okay, or by some property, or by writing a property which is using set theory. Okay, like this is an element using element of, subset of, those kind of operations. We will define other sets. Okay, so once you have rational numbers, you have complex number and all those things. Before that, I will define what is a metric space. I hope all of you know this. Okay, S is any set which is under our consideration, not any arbitrary set. Okay, S is any set, any well-defined set. Okay, okay, and D is a function from S cross S to. Now this is well defined for us. Okay, this is just a positive real line which is well defined. See, real number, for example, we don't know many things about real number. It looks that we are very familiar. For even natural number, we don't know about prime numbers and all. There are many things we don't know, but we know that what are all the natural numbers, right? Okay, we know what are all the natural. We can list it out in some sense. Real number, we cannot do that. You know, it's uncountable, and we don't know what are all the real numbers. In the sense, for example, what are all the rational numbers? For example, I don't think this is well known. Pi plus c, whether it is rational or not, I don't think this is known. Huh? Pi is transcendental, E is transcendental. What about pi plus e? Yeah, do you know that? No, it's not known. Okay. Similarly, log pi, those things we don't know. Well, even whether it is rational or irrational, we don't know. It will be surprising if it is. I don't think it's rational. Huh? Huh? Say it again. What is that? Yeah, probably, but we don't have a proof. That's what I said. Probably going to be is very clear. Okay. Okay. So that is how we have to construct it like this. Okay. So such that it satisfies these properties is a function such that d of xy, d of xx equals d of xy equals 0 if and only if x equal to y. Okay. And 2 d of xy, this is symmetric property, d of yx. Okay. And then the triangle inequality. Okay. Which just says that d of xy is less than or equal to d of xz, d of zx. Okay. Okay. So now the question is, Eh? Z, Y. Yeah. For all X, Y, Z. Okay. So this is a metric space. Okay. So, I mean, this is a metric, the definition of metric. Then we usually call like this, S with D as a metric space. So, example, I forgot to add one more thing, which we'll add in the assignment. If you have a Cauchy sequence Xn, then mod Xn is also a Cauchy sequence, so that you can extend this definition of mod from rational to real numbers. So, we have that mod function on real numbers. Okay. So, this using, I mean, using D, where D of xy equal to mod x minus y, okay, is a metric. This is the basic metric space which you have seen, okay, so this is a metric, number one. Number two, you have C. Once you have real numbers, you can define C. You can call I as, I mean, you need not even know I as root of minus 1, but you can define the multiplication, assuming it's a root of minus 1 kind of thing. Okay, you define the multiplication and then you can get C. Okay, so C with, and you have the modulus function, which is a plus ib, the modulus of that is a square plus b square, square root of that. Okay, so the C with mod. Okay, and so yeah, is it clear? It's a metric. I mean, I hope you know this satisfies the triangle inequality. I hope you know that. I mean, but it needs some proof. Okay, exactly. A plus, I mean, you want to, I mean, you just have to prove that a plus two complex number is less than or equal to mod a plus mod b. You write it as square. Take the square of this a plus b bar, and then individually you do this. Then you get some real part which will be less than this. And I mean, okay, so you can prove it. So I don't need to prove that. Okay. So these metric spaces, you know. So similarly, Rn, Cn. Once we have all these things, Rn, Cn, all these things we can prove. Okay, we have got this. So generally, we have a metric space. We will define it like this. Many metric spaces we deal with are defined through the following. So third example of metric space, V is a vector space. Okay. V is a vector space. Vector space is abelian group with a scalar multiplication and satisfying many properties. See, whenever we have two structures on something, those two structures should be compatible. There is an addition and a scalar multiplication that will be connected by the distributive law, and it will be, I mean, all those things, associativity, all those things are there. Okay, so you know what a vector space is. Okay, then a norm is a function from the vector space to 0 infinity. Okay, is a norm Rm. Okay, if it satisfies 1, okay, norm x equal to 0 if and only if x equal to 0. There is a 0 element in the vector space. Okay, norm x equal to 0 if and only if x equal to 0. 2 term alpha times x for all x in. Okay, alpha times x is equal to mod of alpha times norm x for all alpha. This is a vector space over C or R. You can take any field, but let's, I mean, since we want metric and other thing, we will do this. Okay, alpha is in C or R. Listen, I mean, it's a vector space over R or C. Depending upon that, you take the modulus. Okay, so this is the second condition for a norm. You have a vector space. You have a function from the vector space to 0 infinity. It's called a norm if it satisfies these three conditions. Third condition I'm going to write. The first condition is this, second condition is this, and the third condition is the triangle inequality. Norm of x plus y is less than or equal to norm x plus norm y. Okay. So this is what is called a norm. Once you have a norm, you have a metric. Okay. So this is just a definition. Okay, this is definition. Okay. So define d of xy equal to norm of x minus y. That's all. Okay. This is a metric. So you take any vector space. If you have a norm, just you verify it's a norm. Then you define the metric to be like this. That will be a metric. Okay. So this way you can actually those Rn, Cn, all those things. You can verify that that's I mean whatever we have the modulus using that. But Rn, Cn, I haven't defined the metric. I just said Rn, Cn. I will define the metric now. Okay. So example on Rn or Cn. Okay. Define D1 of any, so two element x bar, y bar, which I mean bar I am writing because it's a vector x1 up to xn, y1 up to yn or something. Okay. This is equal to summation mod of, I will define the norm. Norm or metric doesn't matter. Okay. Norm of x1 equal to summation mod xi. I equal to 1 to n. One second. Where x bar is equal to x1 up to xn in, I mean, x, you take Rn or Cn, so you have a vector x bar which is x1 up to xn. Then you define the norm of x bar, norm of x, I put a 1 because it's defined like this. Okay, I mean, this is just a notation. 1 norm or something. Okay, so x bar, norm x1 bar is summation I equal to 1 xi, norm xi. Okay, this is a norm. You can verify. You can leave it as an exercise. Exactly the same thing, same using modulus as a sum, you can do that. So this is one norm. The second one is norm x infinity equal to maximum of mod xi. Okay. This is also a norm, but you should be a little bit careful while verifying its norm. Where you take the maximum, how do you do that? Okay. So are you sure you are careful, or I should do this? You have done this, okay. Oh, you have done this in calculus. So you have done all these things. Okay. So these norms are equal and you have done.
Oh, sorry.
On finite dimensional, on any finite dimensional. Okay. So these norms, this can be a norm, can be proven through this. But then you want to prove that D2 is a norm. There is D2 I want to define. Okay. 4 or I don't know the number. So on Rn, see, we want to define D2, but for that you need little bit more. You have to prove something called Cauchy-Schwarz inequality. So I give a new example. For example, another example. V is a vector space. Okay. You have seen Cauchy-Schwarz inequality? Proof of it. Huh? In algebra 1 for any vector space. Okay, then there is not much to do in this course, I don't know. Okay, so you have an inner product. Okay, inner product from V cross V C. Okay, C or R, depending upon which vector space you take. Okay, is an inner product. Okay, then norm x2 equal to, or norm x equal to xx. This, I mean, I haven't defined what is an inner product because you said you know it. Okay, so this is supposed to be positive. Okay, you take the square root of this. Okay, so this is a norm x, this is a norm. To prove this is a norm for the triangle inequality, you will require Cauchy-Schwarz. Okay, Cauchy-Schwarz inequality is inner product of xy is less than or equal to norm x times norm y. Okay. Using this, you can prove that this is a norm. So you get a metric from that. Okay. So if you have an inner product space, then you get a metric. So in particular, on Rn or Cn, you can define this norm x2 equal to summation xi mod xi square root of that. Okay. Right? Correct? Right? So where the metric, where the inner product is given by summation xi, yi bar, all those things. Okay. Okay. So using inner product we can get. Okay. So maybe I will give. So you have seen the discrete metric. Okay. Okay. Now I will define something, a generalization of discrete metric. So you have set n S1 cross S2 cross up to SS, where SIs are each SI is a set. Each SI is a metric space. SI DI. No, SI is a metric space. Okay. No, SI is just a set. You have some set S1 up to Sn. Okay, some set, well-known set. Okay, then you define a D, maybe Dn, okay, of some S tilde, S bar, T bar, where S bar is equal to S1 up to Sn, T bar is equal to T1 up to Tn. Okay, this is equal to number of I such that Si is not equal to Ta. You have set S1 up to Sn up to Sn. Any element here will be a tuple like this, S1 up to Sn, T1 up to Tn. Okay. You define the distance between S tilde and T tilde to be number of I such that Si not equal to Ta. When there is only one set, this is just a discrete metric. Okay. I mean, it is just number of, and if it is equal, it's 1. If it is not equal, it's 0. Okay. The number of I such that Si not equal to Ta. So this is a metric. Okay. Then Dn is a metric. I mean, I wrote it because I want to, for the proof we need the n, so I put the Dn there. Okay. So clearly first two conditions are satisfied. I mean, it gives a positive value, and if dxy equal to 0 means the dxy equal to 0 means they don't differ in any coordinate, so they have to be equal, right? I mean, if dn of some S bar and T bar are 0, then S bar and T bar coincides in all the coordinates, right? Okay, so they are equal. So only we have to verify the triangle inequality. Okay, so we use induction. To verify triangle inequality. Okay. So D1 is a metric, I mean, induction on n collection of n sets. Okay. So if you take any set, S is any set, then D1 is just D1 defined through that is just is the discrete metric, right? Which you know already it's a metric. Okay. So assume Dn on any S1 cross up to Sn is a metric. Okay. You want to verify Dn plus 1 on some S1 up to Sn plus 1 is a metric. Okay. I mean, satisfies triangle inequality. Okay. Dn plus 1 on this satisfies triangle inequality. Okay. Okay. So you take ns per bar, which is equal to S1 up to Sn times Sn plus 1. Okay. And some T bar equal to T1 up to Tn times Tn plus 1. I mean, it's an easy exercise. Then, so then you define S bar prime equal to some S1 up to Sn, or maybe R also, some R bar equal to R1 up to Rn plus 1. Okay. So, and then S prime to be, you just truncate at n. Similarly, Tn prime, similarly R prime, and T bar prime to be again T1 up to Tn, and r bar to the prime to the r1 up to rn. Okay. So case 1, if Sn plus 1 is equal to Tn plus 1, okay, then Dn plus 1 of S bar T bar is same as Dn of S bar prime T bar prime, right? Because the last one is equal, right? So this is less than or equal to, because this satisfies this Dn of S bar prime, R bar prime, whatever, Dn of R bar prime, T bar prime. Okay. But then this metric will be, if you, I mean, this may be plus 1 or something. This is certainly less than that Dn plus 1 of S prime, S bar, R bar plus Dn plus 1 of R bar, T bar. Okay. So the triangle inequality satisfied in this case. Okay. Case 2. So if the last element is not equal, and I'll just orally say this, I'm finding it difficult to write. So this will be just this, I mean, this will be, yeah, this will be this plus 1. Okay. Then you write the triangle inequality for this, which will be this plus 1. Okay. And then if it differs here, okay, if it either this should differ here, this r in the n plus 1 place should differ here, or the n plus 1 place differ here. It cannot be same in both the places. Okay. So that you can add that plus 1 to get this. Then there is only one thing remaining, which will be less than the other one. Okay. It's easy. Okay. So you can verify this is a metric. Okay. This is a generalization of discrete metric to the n tuple. Okay. Okay. So we will define one more thing. We have seen sequences L1, L2, LP, L3, L infinity. Okay, we will just define that. Okay. Huh? Not, no, I'm going to define. Well, if you want, see, if you have said something you have seen, so I went very fast. Okay. This also you have defined. I defined this. Okay. So examples of metric space. Okay. Okay. So collection of all sequences xn n equal to 1 to infinity. Okay. Where xn, I mean, we usually take complex number. You can take real numbers. Work with real numbers if you want. Okay. Such that summation mod xn is finite. Okay. This you call it as little L1. All summable sequences, okay, or convergent series or whatever, absolutely summable. Absolutely convergent series, but we deal with sequences. I mean, series is you get it from a sequence, right? So okay, so if you write it as a sum, it's called series, but it's a sequence. So all absolutely convergent. Okay. This is a well-defined one. I mean, okay. I mean the limit of I mean then the limit also exists. Okay. I mean limit of the sum is also exists. Okay. This is no wait. This is a set. This is L1. Okay. On this you define norm of this sequence xn 1 equal to summation mod xn. That's all. Okay. This is a norm. Of course, first thing, if summation xn, I mean, this is positive, of course. If summation xn equal to 0, these are sum of positive numbers, each xn has to be 0. So it's a 0 sequence. Okay. And if you have an alpha here, scalar multiplication, multiply, this is a vector space, collection of sequence is a vector space, and you multiply by a scalar means you multiply each element by a scalar. That is a scalar multiplication. Xn is a sequence. Xn is in C.
finding a set in which the norm of every element is the limit of the.
It's just the sum of that. Yeah. Okay. You just take the modulus of that and sum it. Okay. So that is the norm. It's clear, it's positive, and it is clearly, I mean, it's a positive definite, strictly positive definite. That's what is called the strictly positive definite. Norm x equal to 0 implies x equal to 0 is what's strictly positive definite of the norm. Okay. Or if you have the inner product, it's based on inner product. I mean, positive definite of the inner product. Okay. So if summation xn summation mod xn equals 0 means xn has to be 0, so that's a 0 sequence. So the first one is satisfied. So the second one is if you have a scalar, okay, I will not write everything. Okay. If you have a scalar multiplication, so then you get the alpha here, you will take it as mod alpha here, it will come out as mod alpha here. So second axiom is also satisfied. Third axiom is triangle inequality. That is also clear. Is that clear? You have to verify. Yeah, each one is that, then that's also clear. Okay. Okay. I mean, if you want to take it as finite one, take the I mean, you have to be little bit careful. See, something like this. You have mod xn, n equal to 1 to infinity, mod xn plus, I mean, mod xn plus yn, okay, is less than up to n. You take up to n. I don't know whether it is needed. Summation mod xn plus summation mod yn. This is the triangle inequality you get. N equal to 1 to n, n equal to 1 to n. Okay. Then by taking n, these are all positive. By taking n equal to infinity, you get the, you can put it infinity here. Okay. Now you take the, now here it is just a number. For each n, this is less than that. So you can take to be infinity. It's just little bit careful. I mean, even when you take the least upper bound and all those things, we will be careful. When we do that, we will be careful. You should be just careful about this. Okay? I mean, it will mostly work, but this is the argument. Okay? So this is a norm. Okay? This is one norm. So example 2, you take all xn, okay, sequences such that xn is bounded. Bounded. Okay. All bounded sequences. That's also a vector space. You can, I mean, addition and all those things, it's just the point-wise addition. Okay. Sequence xn plus sequence yn is xn plus yn. And scalar multiplication, you just multiply each element in the sequence. Okay, the vector space structure is clear. Okay, I hope everybody is comfortable with this. So vector space structure is clear. Okay, so this is all bounded sequence, which is a vector space over complex number, if they are all complex number or reals, whatever you want. Okay. Now you define norm, this, take this sequence xn, the infinity norm. Okay, here you can't take maximum. If it's a bounded sequence, no, you can, I mean, you have to take the supremum. Maximum may not exist. Okay. I mean, maximum may not exist as a member in this. That maximum, when you have a set, by maximum you mean an element of that set. Okay. So maximum may not exist. For example, 1 by n, which is a bounded sequence, minimum doesn't exist for that. Okay. So supremum of mod xn. Okay. Okay. Over here. So this is a norm you have to verify. Okay. First thing is, I mean, it's clear that if, for 0 sequence the norm is 0, and if the norm xn infinity equal to 0, the supremum of mod xn is 0, so everything should be 0, because, I mean, it's less than the supremum, so it should be 0 sequence. And if you have the alpha here, supremum, the alpha will come out. Okay, that is clear to you. The alpha will, I mean, mod positive alpha will come out. Positive alpha, mod alpha will come out. Okay. So then you have to talk about. So then you have the triangle inequality. You have xn plus yn is less than or equal to mod xn plus mod yn. Okay. Okay. This is true. So this is less than or equal to supremum of mod xn. See, here is what we have to be careful, as I said. Supremum of mod xn plus supremum of mod yn. Okay. This is true for all n. Here it is just a number. Here it is just some number. For each n, this is true. Now you have to take the supremum here. Okay, I mean, you have to write the next step. Okay, that is how you should prove. Okay, I mean, this is just I am telling you because this is the first class. I have to tell you, you have to be careful like this. Okay, since if you have seen it already, you are very clear about it. Then there is nothing to worry. Okay, so we have the triangle inequality. We take the then this is less than this. So this is less than this for all n. Now you take the supremum over here, which will be less than this. So this implies that I mean, this implies that norm of two sequence xn plus yn infinity is less than or equal to the individual. Okay. So triangle inequality is satisfied. So now you can, so this is what is called L infinity. L infinity is all bounded sequences. L1 is all summable sequences. L2 is all square summable sequences. Okay. And the proof for L2 is very easy because it will be an inner product and it's more easy. You don't have to verify much. If you have the Cauchy-Schwarz inequality. So, okay, I will stop soon with this. Okay, all those xn such that summation, I'm using mod xn square because it may be complex number. If it is real number, you don't need that. Is less than infinity. This is what is L2. On this, you define norm xn 2 is equal to summation mod xi square root of that. This you can define, but for this you just define, you take some sequence xn, take some sequence yn. The inner product is summation xn yn bar. You just verify this is an inner product. To verify this is inner product, we are doing mathematics. I mean, mathematicians are wrong in defining the inner product. For in mathematics, the first one is linear. I didn't say, since you have seen inner product, I didn't go through this. In mathematics, the first one is linear, second one is antilinear for complex one. In physics, it will be the other way, and actually they got it right. Okay, in physics, that is the right way to do it for some reason. Okay, this will become complicated when you use ket vector, bra vector. This will not be. I mean, the physics will be convenient. Okay, and I mean, from K.R. Parsaradhi, a mathematician, he used to say that physicists got it right, and that's the only thing they got it right. So, okay, so this is an inner product. If you have an alpha here, it will come as bar. If you have an alpha here, it will come out as it is. So it's linear and it's antilinear in the second one, and all these things are clear. And I mean, inner product has to satisfy. I didn't write down all the properties. Okay, this is same as yx bar. That is also satisfied. Okay, and what else? So this is clearly this gives a norm. So this is L2, small L2. You will see a capital L2 also. Okay, using functions. So this is maybe in the next class I will define. Okay, so these are all the examples of metric space. Okay, we will give more examples in the next class. Okay, we will meet on Friday, hopefully.